All right, welcome to Unit 2. Congratulations on getting through Unit 1. I don't think it is actually the easiest unit. It certainly isn't going to be the hardest unit we do, but it is kind of a quick jump into 30-1. This unit I would say is probably a little bit easier, but this is really one of the most fundamental ones to set us up throughout the whole unit. Of course, we needed all the function stuff from last unit as well. This one's all about transformations. It's all about that formula that I've got written on the sideboard to your left, if you look over there. So we're going to be learning how to understand that and all the things that go with it. There's all this stuff here, but first let's talk about what we did last year. So, well, not we, but you. Last year you talked about the vertex form of quadratics, so you were looking at this thing. You probably used y instead of f of x though, but you should be pretty familiar with this form, and you should know what all the different variables do. You learned that the vertex was the point hk, and you learned that the value a determines whether it opens up or it opens down. So this implies whether it opens up versus it opens down, and it also implies the vertical stretch or vertical compression, so how steep or how flat it's going to be as well. So if it was an A of 0.01, it would be a really wide but facing upwards parabola, and if it was A of, say, -7, it would be aiming downwards and it would be really, really steep. So this is in the same kind of form that we're going to be looking at for transformations. Basically, we're going to be looking at these three variables, and we're going to be adding another one as well. We're going to have a b value in there for horizontal stretches and compressions. They don't matter so much in parabolas, so that's why we didn't talk about them last year. But we're going to have one more variable in there as well. And the important thing to think about for these things, there's two ways to do it. If you saw something like f of x equals 2 x minus 3 squared plus 1 or something. So you would have the vertex at 3, 1. Now there's two ways to think about this. Some people see it just as this is one parabola. I want to be able to build it from scratch. So I would have to draw my little thing. I'd find where the vertex is over at 3, 1. And from there I would go up, and it would be a step of 1 up, 1 to the right, 2 up, 1 to the right, 6 up, I think, and it would go up like that. It would be pretty steep. We don't want to see this as an independent parabola, though. We don't want to just analyze it in terms of its key features. We want to see all of the parabolas as transformations off of the original parabola. So the original parabola is y equals x squared. And that one starts at the origin. And this one should be very familiar. It goes through the point 1, 1, -1, 1, and 2, 4, and all those squared values. So we want to actually see this one as the original parabola, and it's actually just being transformed. So what are we doing to it? Well, we're shifting it up by 1, is what we're saying. So this one over here actually takes all of our y values and it's going to shift them up by 1. And this value in here means it's actually going to be moving to the right by 3. Rather than just finding where the new vertex is, we want to actually treat it like taking the original vertex and shifting it to the right by 3. So all these things we're going to see as transformations. It was really easy to do the transformations because the vertex started at the origin to begin with. That's why these values were so easy to do it. That won't always be the case. But that's what we're going to be doing, and we're going to be doing it not just with quadratics, but we're going to be doing it with all of the functions. That's why we're going to be doing it in the general function notation, because the same thing holds true for all of ours. We're going to be doing it with absolute value functions, lots of different ones. So we got the absolute value x, we got root x, we've got our rational function 1 over x, we've got our x squared, we've got our x cubed, we've got all of our polynomials, and we're going to be adding some extra ones on later this year. We're going to be adding on sine of x, we're going to be adding on our logarithms, ln of x, and some other functions. Can't really think of any right now. That's pretty much all of them, I think. I'm probably forgetting one, but those are the big ones. Okay, let's jump into it. This first section I think is pretty easy, so I'm going to go fairly quick through it. You can always pause the video if you need a bit more time. Take a bit of time, read the top. I don't think there's anything too special in there, so I'm going to jump right into it. A translation is a transformation which slides each point from the figure the same distance in the same direction. So you kind of talked about this in grade 9, and I don't remember if this came up in grade 10 at least, but in grade 9 we talked about translating, shifting like a polygon or something on a grid to the right, shifting it down, reflecting it. So you've done transformations in the past, but now we're doing it with functions. So comparing graphs, the first type of shift we're doing. So this is the original. We want to compare that to, and they give you two different versions of this, but basically it's all about this k value here, and it means the same thing. I actually really like this one, and I'm pretty much am always going to talk about it this way, and almost everyone I know has talked about it this way, but for some reason the book you have almost prefers it this way a little bit. I don't know why. But it means almost the same thing. So y minus k equals f of x. All you got to do is add the k, move it to the other side. Y equals f of x plus k. And that's the way we have it on our board to the left. So if we add a value outside the function is what we're doing. So how does that do it? Complete the table of values. This is our original one. If it was y minus 3 equals x squared, again, I'm going to shift this to the right. So that actually means x squared plus 3. So you would take all your original x squared values, which we actually have over here, and we just have to add 3 to them. So this should be 12. This should be 7. 1 makes 4. 0 makes 3. And then 4, 7, 12. Because it's a parabola, it's going to repeat itself. And then if we had to graph that, which we're going to do later, so at 0, it's up at 3. At 1, it's up at 4. At 2, it's up at 7. Basically, everything's just being shifted up exactly by 3 points. And it repeats on the other side. So that should be our first parabola. Draw some arrows on there. And that is y equals x squared plus 3. I'll try and use another color for the next one so it doesn't get too confusing. So now in the next one, this is y plus 3. Again, I'm going to move it to the other side because I prefer seeing it that way. But really, it should be easy to see it both ways. So y equals x squared minus 3. So this time we're taking all of our original x squareds. So again, you would still plug in negative 3 to the x. Negative 3 squared is positive 9. But this time we're subtracting 3 from our answer that we got here. So this is going to go down to 6. This is going to go down to 1. It's going to go down to negative 2, negative 3, negative 2, 1, 6. Just taking away 3. Graphing that one, it should be 1, 2, 3 down. It's going to look roughly like that. So, use the table of values to graph each and label the functions on the grid. Done that. In the second table, y has been replaced by y minus 3. What's the effect of this on the graph? This is a vertical translation or shift. Either word is just fine. I use translation up there. I'm just going to use shift because it's a bit faster. Usually we eventually change that. 3 units up. A vertical shift or a vertical translation, 3 units up. That means all of them are just sliding straight up. The third one is y plus 3 or minus 3 on this side. What's the effect of that? That's a vertical shift. 3 units down. Good. Sometimes I see people use just v.s. vertical shift. Actually, you probably want to do t for that translation because the next one that we learn is a stretch or a compression. So I think they do vertical translation. Yeah, they use v.t. Use a graphing calculator to graph the following functions. There's going to be a lot of graphing in this unit. Your graphing calculator is okay. I use Desmos pretty often, and I'm going to walk you through some of these translations when we get together tomorrow. And I'm going to use Desmos for it. Desmos is a website on the computer. It's easy to bring up. It's easy to use. I think Haley and Sarah have used it. I'm not sure if you've used it before. But it's pretty easy to use. So if you wanted to pull that up, you can do that for these ones. The graph of absolute value x looks like that. It's just a nice V. We're just doing sketches here. Absolute value of x plus 2. So you're going to take all the original values, you're adding 2, so it's going to be a vertical shift up by 2. Absolute value subtract 3, so it should come down by 3. Might want to write in this is 2, this is negative 3. It's good to put in at least a key point. That way you have some kind of grounding for your graphs. It's just not all over the place. The equation y equals absolute value of x plus 2 can be written as, it can be written the other way. Y minus 2 is equal to absolute value x. How does the replacement of y by y minus 2 affect the graph? Well, this is again a vertical shift. It says y minus 2, but it's actually going up. Vertical shift up 2 units. The last one is minus 3 on this side or plus 3 on this side. This is going to be a vertical shift down by 3 units. That's why I prefer, I don't know why, maybe it's just habit for me, but I always prefer seeing it that way. I think it just makes more sense. But they have a reason why they do it the other way. Using the results from part 1 and part 2, answer the following questions based on the graph of y equals f of x. What's the effect of the parameter k? So this is, again, all of these values that we've been working with are just our k value. We're always going to call it our k values. What's the effect of it on the function? This is a vertical translation. And if it's plus k, then it's up k units. What's the effect of k if it's y minus k? That's actually the same thing, right? That's just moving the k to the other side. So this is actually the same. It actually depends on what k value you have. I probably shouldn't have said up. If k is positive, so it remains positive k, then it's up. If it's plus negative 2 or something, then it's actually going to be down. So up or down, depending on if k is positive or negative. I thought this one was going to have the negative k for some reason. Complete the following statements. Compared to the graph of y equals f of x, the graph y minus k equals f of x results in a vertical shift vertical, the translation's over here, a vertical translation of k units. If k is positive, so in this one, if k is positive, that would be y minus k. That over here would be plus k. So this is always backwards. And they actually write it right in the equation. This is something tricky to see. We'll see it better down here. If k is a positive value, the graph moves up. If k is a negative value, the graph moves down. So the notation y minus k equals f of x is often used instead of y equals f of x plus k. I don't know, I guess maybe it's different place to place depending on where you go to school. To emphasize the fact that this is a transformation on y. that this is affecting the y values, not affecting the x values. I just prefer to see it as whether it's inside the function versus outside the function is what I like to focus on over here. So if it's inside the function, it affects the x values. If it's outside the function, it's going to affect after the function has happened, so it affects the y values. The concept of replacing y by y minus k is very important in this course. Yeah, all of our transformations are. There's 4 of them. So if it's on this side, it says y minus k. So if k is positive, it'll be subtract over here, and it actually goes up. Over here it says plus k, so if k is positive, it's positive and it goes up. So either way, if k is positive, it's going up. If k is negative, it's going down. The fact that this one has the wrong sign is written right into the equation itself. So this would be y minus negative 2 would make it y plus 2 would mean it's going backwards. That would actually be a k value of negative 2. So I prefer to see it this way so it's not backwards, but when we get to our next one it will always be backwards anyway. So we have to be careful with that. That's probably confusing. I'll go over that more in detail as we go on. Okay, even quicker. Let's do the same thing. We have a new variable now. It's h. Sorry. So now it's on the inside of our function, and this one is written backwards, and it's pretty much always. I don't think anybody ever does it on the other side. So you'll always see it in here inside the function, and you'll always see it with the minus sign. So x squared, we've already talked about this. If it's x minus 3, that's actually a shift to the right by 3. So everything is moving to the right, and they've actually done that for us. They've actually changed the x values to the right. So if you move it to the right, it should have actually the same y values. So the original origin was 0, 0. Now it's 3, 0. Shifted to the right already. If it's plus 3, that means it's moving to the left, and they've done that for us already. So this again should be the same y values. 16, 9, 4, 1, 0, 1, 4, 9, 16. So those are our 2 different ones, and now we have to graph them. So number 2 shifted to the right. 1, 2, 3. I'm just going to sketch it to be quick. So that is y equals x minus 3 squared. We should hopefully remember that from last year. The one on the inside is backwards. So minus 3 is right by 3, plus 3 is our h value. H is plus 3, but it presents as minus 3 because minus is in the equation. The other one shifted the other way. And that's our y equals x plus 3 squared, which means the h value is negative 3. Okay. In the second table, what's the effect? This is a horizontal shift or translation. Three units to the right. In the third table, it's x plus 3, which is a horizontal shift. Three units left. Good. Use a graphing calculator to graph the following functions and observe the effects. So you should do this again with Desmos, and I'll actually show you a better way to do that when we hook up again together after I'm done the other lesson. Root of x, so it should be something like this, is the original function. In this one, it is shifting to the right by 4 because it's backwards. So that one should be like that. This one is to the left by 2. So that one should be like that. Something like that. Based on the graph y equals f of x, and using the results of part 1 and 2, describe the effects of the parameter h. So what does H do? H controls the horizontal shift. Horizontal shift. So it just slides it left and right, is what the H value does. Just like in our quadratic, but it's actually true for all of our functions. If I'm going too fast, just pause it at any point. I know it probably would take longer to graph these, so just pause it if you were graphing them. Complete the following statements. Compared to the graph y equals f of x, the graph y equals f of x minus h results in a something translation, horizontal translation of h units. If h is positive, the graph moves right. I know we said it's backwards, but this is the really tricky part. It looks backwards when you actually see it. So if it says x minus 2, then it's going to look backwards, it's 2 to the right. But the h value is the correct way around. If it said x minus 2, the h value would be positive 2. Let me actually write that. So if it said x minus 2 squared, the h value is actually equal to positive 2. So the equation looks backwards, but the h value is the right way around. So if h is positive, it moves to the right. If h is negative, it moves to the left. Good. Replacements for translations. Given the function y equals f of x, replace y with y minus k. Describe the vertical translation, y minus k equals f of x, or I prefer this one, of course. Describes a vertical translation. We've already talked about this. We've already talked about this. This is just summarizing. In general, so this is combining them together now. This is the formula we like so far. So for every single function, if it's the function of x minus h bracket plus k, so h on the inside, k on the outside, then these things are true. K is positive, it moves up. K is negative, it moves down. And not just that, it moves up or down by k amount. Same thing here. If h is positive, it moves right. If h is negative, it moves left by h amount. So that's our vertical shifts. Okay, class examples. What happens to the graph? These should be pretty quick, I think. This is actually, it takes a while to get really comfortable with it, but it should be a fairly simple concept, hopefully. And definitely by the end of the unit it will be. What happens to the graph of the function y equals f of x if the following changes are made to its equation? Replace x with x plus 2. So that's on the inside, so that's right 2 units. A shift. Replace y with y minus 8. So in my head, I always do it the one way. So that means the 8 goes to the other side. So you're adding 8, really. If you want to think of it, if you want to actually get used to it this way, then you have to think of it backwards this way, just like the other one too. Oh wait, replace x with x plus 2. That's actually 2 units left. Hopefully you're screaming at me right now. Because that's a h value of negative 2 then, because then it's negative negative to make it positive. So that actually moves it left. Same thing over here. If you put it in here, this is actually backwards, so it should be up 8. Of course, it's a shift. Describe how the graphs of the following functions relate to the graph of y equals f of x. Y equals f of x minus 3. So this is 3 units right. Shifting right 3. I'm just going to do it super shorthand to be fast here. This is up by 4. That's a k value of plus 4. This one here, this is 2 different things now. This one first, that's really a h value of negative 10, so that's left 10. Left by 10. This one over here, it's like plus 1, or it's backwards 2, so it's plus 1. So it's going up by 1. Left by 10 and up by 1 in that case. The point 2, negative 3 lies on the graph. State the coordinates of the image point after it's been transformed. So you can do this to every individual point on the graph. We usually use just the key points, like the vertex. Every graph has some key points that we like to shift. But we can do every point that way. So in this one, why don't we state the transformation, then state the new point. So in this one, it's actually going down by 8, which makes the new point 2, subtract 8, that should be negative 11. This one here is going to be moving right by 7, up by 5. So again, we're starting with the same point. So this changes to 9, and this changes to positive 2, are our new points. So shouldn't be too hard. Write an equation of the image after each transformation. A horizontal translation of 5 units left. So that's y equals f of 5 units left, so x plus 5, because it has to be backwards. Some people, when they're just starting out, they actually write it this way. Y equals f of x minus our h value, because the formula always has a minus there, and our h value is going to be negative 5, right? So some people would sub in negative 5, kind of like that. And that is the first step to the substitution, but hopefully you can very quickly realize that it should look like that. But if you want to start out doing it a little bit slower, you can. Translation 3 units up, well, that's going to be f of x plus 3 on the outside. Y equals. You have to use y equals, you can't use f of x twice. So if you are talking about the translation on the function, you actually need to use a y as well. It's a little bit silly that way. A translation, m units right and p units down. So y equals f of x, m units right, so minus m is positive. And p units down, so you actually have to subtract p, or add negative p. Should be that one. Last page. Given the graph of the function y equals f of x, sketch the graph of the indicated function. So this one is 2 units right. So we're going right by 2. This is actually a common thing that we do. We're going to do those are actually called our parent functions, what I talked about at the beginning. These guys right here. This is our set of parent functions. These are the original versions of all of our different types that we're going to be transforming. So we're going to be using a lot of these, but in this unit, and especially at the start, you might see these things, and they're just random functions that you have to transform. So there's no good way, you can't do it algebraically, you actually have to just go through the picture and actually move the points as you go. And that can be a little bit challenging sometimes, but usually not too bad. So this one's shift everything to the right by 2. 1, 2. That one's new points there. 1, 2. 1, 2. There's actually a point there still, but there's also a point there. And connect the dots in the same way. So that should be that one. This function here, we're going to be going to the left by 3, and we're going to be going down by 2. So 1, 2, 3, 1, 2. That's that new point. 1, 2, 3, 1, 2. A little bit hard to see. Should look something like that. Always check it over when you're done. If you've only done shifts, all these are horizontal and vertical translations. it should have the exact same shape. If the shape looks funky, then you probably put one of the dots in the wrong place. Okay, replacement notation and mapping notation. Do not confuse mapping notation with the notation we have used for replacements. Replacement notation is what we have been using. Mapping notation works a little bit differently. Consider the example where the graph y equals f of x is transformed to the graph y minus 2 equals f of x minus 3. In this example, the replacement of x and y might be written as x minus 3 and y minus 2. Under this transformation, all points on the graph of f of x will move 3 units to the right and 2 units up. So even though we're writing it this way, both of these things are going to look backwards, is what it's reminding you of. So you don't actually take your x values and subtract 3 from them. You actually have to add 3 to them so that you get back to the original number. Because if you're trying to get to the answer of 6 or something, if you put the same number in here, you'd end up lower. You have to actually add 3, go to 9, and then you'll subtract 3 to get to 6. I'm probably explaining that too fast. But yeah, these are backwards. So it doesn't mean you subtract 3 and subtract 2 from your numbers. You actually have to add, move 3 units to the right and 2 units up. So you have to actually add them. So a point with coordinates 4, 6 will actually be translated to the point 7, 8. So in general, so this is our new one. This is mapping notation now. If you wanted to do it with mapping notation, which means writing every coordinate with how they change, it's actually going to be x plus 3, y plus 2. So every single point will be added 3, 2 on the x and added 2, 2 on the right. The mapping notation for this translation may be written as xy equals, or xy implies, or transforms to, that's the best way to interpret that, transforms to x plus 3, y plus 2, implying that the point with coordinates xy is translated to the point x plus 3, y plus 2. Not as complicated as it sounds. Notice that the mapping notation is not the same as the replacement notation. So these things are not the same. You have to be careful. So in this form, it's the right way around. In this form, this one is backwards, right? This isn't what we were looking for. So the mapping notation is equivalent to the replacement notation. These things are true. This is the right way to think about it. This way in mapping form, so 3 units up, 2 units to the right, is the same way in replacement form. If you're putting it into the equation, it should say x minus 3 and y minus 2. This is actually just another way of saying what we've been saying, which is when you put it into the equation, the x's are always backwards looking. And if you put the k value on the y side, it's going to be backwards looking as well. State the coordinates of the image point negative 3, 5 under the translation described by x. Y goes to x minus 7, y plus 4. So this means 7 units left, 4 units up. This is the right way around. So every x value, you're going to take away 7. You're moving it to the left 7. You're moving it 4 units up. So now let's write it the other way, though. 7 units left is going to look x plus 7. 4 units up actually is plus 4 on this side. It would be minus 4 on that side. So this one's actually the right way if you see it on that side. Write the equation of the image y equals f of x after the translation. So this is going to be 6 units left and 1 unit up. So this becomes y equals f of x plus 6, or minus negative 6. Again, if you want to do it the slow way, because the formula is minus h plus k, and our h value is negative 6, and our k value is positive 1. So then you can sub these things in. So x minus minus 6 is f of x plus 6. And k is plus 1, so plus 1. So that's how you switch between the two forms. It's really weird that it's backwards, but the way, if I always write it the way that you see it on the other board, a b x minus h plus k. Sorry, I got a cough. If you always see it this way, then it's just everything inside the function will always be backwards, and everything on the outside will be the right way around. Okay, there's the assignment.